Hello everyone, welcome to the next lecture. We are talking about diodes. In the last lecture we started with, we developed this small signal model of a diode, and we analyzed that we can model diode as a resistor for small signal operations. Today we are going to do a few examples that will help build those concepts. Alright, so let's start with an example. Alright, excuse me, consider the following circuit here. So we have our resistance, 10 kilo ohms, our supply, a potential drop across the diode, VD, and then the current ID is flowing over here. Okay, so the first thing is we can make an assumption that diode has 0.7 volts voltage drop at 1 milliamperes. Second thing that is given in the question is this supply V positive is 10 volts DC and have 1 volt peak sinusoid superimposed. Right, so it's 10 volts plus 1 volt peak sinusoid superimposed on that 10 volts. We are interested in finding DC voltage of diode, which is VD. So we are interested in finding VD and amplitude that is superimposed on it. Amplitude superimposed on it, right? Or the sine wave that is appearing across it, or sine wave appearing across it. So we are interested in finding that out as well, right? So which will essentially be VD of t. We are also interested in finding out that incremental value. All right, so let's do the solution. In the solution, so we can see that the total instantaneous voltage at the diode will be the sum of the DC voltage plus the time varying component, right? So this is DC diode voltage, and this is time varying sine wave signal superimposed on the DC voltage. So we are interested in finding this thing out. All right, so let's let's consider the DC quantities only. If we only consider the DC quantities, then from the assumption we can know that our VD was 0.7 volts. Sorry about that. And if VD is 0.7 volts, let's find the value of ID current. So ID can easily be found by using Kirchhoff's law. So ID equals 10 volts VD minus potential drop across the diode 0.7 over R, which is 10K. 10 minus 0.7 over 10K is going to come out to be 0.93 milliamperes. So the DC value of the current came out to be 0.93 milliamperes. So these are the two DC values that we found. Now we can see that since our current value 0.93 is close to 1 milliampere, so we don't need to probably do this iterative analysis in which we can refine the value of ID and VDs again, right? So since this value is close to 1 milliamperes, so diode voltage is very close to assumed value of 0.7 volts, right? Since both of the current values are very close to each other, so this means that our VD values will also be very will be even more closer to each other. So that is why we don't need to do iterative analysis. We can stop that analysis in order for finding these DC quantities here. So by now we have found the DC quantities. This means that I have found this operating point values of VD and ID, which is 0.7 volts and 0.93 milliamperes. Just consider them as opposite. So this is on y-axis and this is on x-axis of the IV plane. All right, now let's find the diode incremental resistance. So considering these two values, the diode incremental small signal resistance will be, we saw that what is the value of RD? The RD equals VT over ID. VT is 25 millivolt at room temperature, and ID is 0.93 milliamperes. So the value of the RD is going to come out to be 26.9 ohms. So this means that I can model my diode with this resistance RD for small signal operation. Right, okay. So the question was, I was interested in finding both the values, this DC value and this time varying value. We find it up the value, the DC value, which is 0.7 volts. Now I'm interested in finding the value of VDT, right? So to find VD of t, we can use small signal equivalent circuit model. What was a small signal equivalent model? We saw that we have a resistor, and instead of a diode, we can use this value of the RD, which is over here 26.9 ohms. And the potential drop across this will be equals to VD of t. So this is what we are interested in finding. This is R, and now this is also the changes in the values. We saw that the small change is 1 volt peak sinusoid that was superimposed. So this Vs over here of t over here will be equals to 1 volt peak sine wave. All right, so we can easily find the VD of t by a voltage divider rule over here. So VD of t equals, and this is again the peak value of that. Peak will be equals to Vs value, peak value, into into RD, which is 26.9 divided by 26.9 plus, what is the value of the resistance? Resistance is 10 kilo ohms, 10k. So if I will put 1 volt here, 26.9 plus 10k, the answer is going to come out to be 2.68 millivolts. So this is the value of the VD of t. So this is how we can find the time varying component of the VD of t that is appearing across the diode, and the value of the DC value of the diode potential drop. All right. Since now important thing to see over here is that since our voltage that will come out to be 2.68 millivolts is a very small voltage that is being superimposed on our potential drop across the diode, which was 0.7 volts. Since a very small voltage superimposed on that, so our small signal analysis is justified, right? It's a very small signal, so small signal analysis is justified. All right. Now there is one important realization. So by the way, this is how we solve the circuits, the small signal circuits, where we need to find the time varying components on the top of the operating VD and ID values. Okay, so one more important realization that you may have already realized by doing this example is a very important thing came out of this example, and that is we can see that as we so the value of the Vs was the value of the V positive was 10 volts, and the incremental value of the V was 1 volt peak, right? So if there is a 10% change, right, and this represents a 10% variation, and let's talk about the VD. The VD was 0.7 volts, and delta VD, which is essentially VD of T, it was 2.68 millivolts. This represents approximately a 0.4% variation. So this is an important realization right over here, that using a diode circuit, if we have huge changes in the voltage values that is powering up the circuit, over here V positive, if there's a 10% change, even a variation in the signal of that power that is powering the circuit, the output, we only see a very small change in the output. So this is another application of the diode, that we can use it for voltage regulation, right? We can use it as a voltage regulator. That even if there's a, so what we are essentially doing this by using the diode circuits is, we can develop a voltage regulator circuit which will make sure that my output voltage will always be very constant, or there will be a minimal change in the output voltage, even if there is huge variations in my supply, in my power supply. All right. So now this is where we're gonna move next. Now we are gonna talk more about the voltage regulators. So let me define the voltage regulator in slightly more detail. Right, so the voltage regulator requires output voltage remains as constant as possible for the following conditions. One, if there is any changes in load current, drawn from output terminal, and changes in DC power supply voltage feeding the circuit. Right, so this is what the voltage regulator is doing. So we build this voltage regulator circuits using diodes, and that will ensure two things. The first thing that it will ensure is, if there is any changes in the load current that our load circuit is drawing, for example, if the load resistor, the load circuit will start to draw more current from the output terminal, our output voltage will remain the same. So that is one important consideration while building voltage regulators. The second thing voltage regulators do is, if there is any changes in the power supply voltage variations, output voltage will remain the same. And we saw this example earlier. In this example, it was an example of the second thing, that we had this 10% variation in the power supply that is feeding the circuit, and our output just has 0.4% variation. So that was a pretty good voltage regulator. Now we are going to do another example of a voltage regulator. All right. So let's do this example. Okay, so in this example, what we are going to do is, we are going to consider the following circuit. Rather than using one diode, I have now 3 diodes available. The resistance attached over here is 1 kilo ohms, and the potential drop across over here, that's called V naught. Right over here, ID Let's call this as I. And this is 10 volts plus minus 1 volt. All right. Now, if we look at the circuit, we have 3 diodes. Our output is being, our V naught output is being collected across all the 3 diodes. So we want our output V naught to be as constant as possible for any variations in the input. So the first thing that we wanna do is over here that we can see that the supply that is feeding it is 10 volts, and there's a 1 volt variation in it. There's already a 10% variation in it. So we want to see that how much that variation is gonna cause the effect or effective change in the output voltage, right? So we want to calculate percentage change in output voltage V naught caused by first, or let's call it as a 10% change in power supply, and this is what we have done, 1 volt here, and second, connection of a load resistance, connection of a load resistance. So what we are interested in finding out in this circuit is how effective this circuit is in terms of providing a change in the output voltage. Can we use that as a voltage regulator or not? And we are going to do it by trying 2 things. The first thing is by changing the input voltage that is feeding the circuit, the 10 volts thing. We are going to produce a 10% change in that and calculate the output voltage. Then as a second thing, we're going to connect a load resistance, 1 kilo ohms, that is going to draw its own current. So that will change the current value that is being drawn from the circuit. And then we will again find the output voltage, and we will see what is the difference in the output voltage now. All right, so the first important thing that you can that is probably given in the question as well is, and this circuit is used to provide a constant voltage of 2.1 volts. Right, so this is a circuit that is being used as a voltage regulator to provide a constant 2.1 volts. And essentially we can easily see it as well. Even if this is not given in the question, you can easily find this out by assuming a potential drop across every diode to be 0.7. We have 3 diodes, so the total potential drop across all the diodes is going to be 2.1 volts. Okay, great. So this is output voltage that we have, 2.1 volts, and we want to find out what is the variation in this 2.1 volts is going to be if there is a 10% change in supply and when we connect the load resistance. So let's do this analysis. All right. In the A part, right, we have no load is attached, and the diode is forward bias. We can see that in the circuit. It is connected to the 10 volt supply, right? Okay, and so the diode, let's find the diode current. All right, so the diode current will be, let's find this I. Okay, and in this example the same current is going to flow through the resistance and through the diodes as well. Right, over here I is going to be equals to ID. Okay, so let's find ID. ID equals to be 10 volts minus 2.1 volts potential drop across the diodes and divided by the resistance. So it is going to come out to be 7.9 milliamperes. Right, so the value of the ID is 7.9 milliamperes. Sorry. So once we find this value, the next thing that we need to do is find the incremental resistance. diode small signal resistance. So let's find the value of RD. We know that RD equals VT over ID. So 25 millivolts over 7.9 milliamperes. It comes out to be 3.2 ohms. Right? Since we have 3 diodes in series, right? So total RD will be, right? So the total RD will be 3 times 3.2, it will be 9.6 ohms. So the total resistance, incremental resistance, is going to be 9.6 ohms. All right. So now let's solve. What we wanna find change in V naught for a 10% change, and let's define that change to be the peak to peak voltage change in input voltage. Right, so this is what we are interested in. So if I will make a small signal model circuit, I have converted all the 3 diodes into their equivalent resistance, which comes out to be 9.6 ohms. So we have 9.6 ohms. This is the value of RD. And this is going to be the incremental change in the output voltage. This is going to be R, which is 1 kilo ohms. And this will be the change in the supply voltage, which was, right, it was 10 volts and 1 volt peak. It was 1 volt peak, and so correspondingly it will be 2 volts peak to peak. And we are interested in finding the change, the peak to peak, 10% peak to peak change. So it will be 2 volts peak to peak. All right, so delta V naught peak to peak will be equals to Vs peak to peak multiplied by R. So diode small signal, let's, in order to avoid the confusion, I'm going to call the 3 diode resistance just to be a small r. Right? Assuming that RD to be a small signal diode resistance for a single diode, the total resistance for all the 3 diodes is going to be represented by only R. All right. All right, so it will be R over R plus R, capital R. Sorry. So it's 2 volt over 9.6. 9.6 plus 1000. The answer, the change in that is going to come out to be 19 millivolts peak to peak. All right. So this shows that with a 10% change in power supply, if there was a 10% change in power supply, the output will change by plus minus 9.5 millivolts, or approximately 0.5%. There is going to be approximately 0.5% change in the output voltage. Again, our V naught was 2.1 millivolts, right? And our peak to peak change is 19 millivolts. So the peak value, so this is going to be equivalent to 9.5 millivolts peak to peak, or only 9.5 millivolts peak voltage. Now again, important thing to remember is this is a change across all the 3 diodes. Such a change across individual diode will be 9.5 divided by 3. It is going to come out to be plus minus 3.2 millivolts. All right, so this is going to be the incremental change across individual diode that will change with respect to a 10% change in the power supply. So we realized that this works as a pretty good voltage regulator. In terms of this is a 10% change in the supply voltage, we are going to have a very small output change, around 0.5%, across all the three diodes. Across all the three diodes, it is 9.5 millivolts peak and 19 millivolts peak to peak, and across an individual diode, it is 3.2 millivolts peak change. Now let's do the part number B, where we are interested in finding again change in V naught when RL 1 kilo ohms is connected. Okay, so our circuit will change now. So what is going to happen now is, now we are going to have a resistance attached over here as well, RL 1 kilo ohms. Also, now the interesting thing is that when you're going to have a resistance that is attached to the circuit, sorry, you're going to have an additional current that is going to draw. Right, so this RL will draw an IL from the output. Okay, so RL will draw IL from output terminal. Right, so we know that our so current through the diodes, initial current through diodes was, what was initial current through the diodes? It was 7.9 milliamperes. Okay, now current drawn by load resistor. So the current drawn by the load resistor is going to be total potential drop across the diode, V naught over RL. Let's first write this. So 2.1 divided by 1K, so it will be 2.1 milliamperes. So initially the current that is flowing through the resistor and the diodes was 7.9 milliamperes. And now out of that, once we will connect the load resistance, 2.1 milliamperes is going to flow through the load resistance. So the current through the diodes will be reduced. So by connecting RL, current through diodes will be reduced by 2.1 milliamperes. Right, so there is going to be a reduction of 2.1 milliamperes. Now, so the total diode current now that is going to flow is, the initial current was 7.9 milliamperes minus 2.1 milliamperes. So the current through the diodes now is going to be 5.8 milliamperes. And the current that is supplied by the 10 volt supply is going to be 7.9 milliamperes. So now we can see the difference in between I and ID. Right, so that is why they were labeled separately to solve the second part. In the first part, when we did not have a load resistance, this I and ID were the same. However, when we connect the load resistance, the total current I was 7.9 milliamperes, but 2.1 went through the load resistance and rest of that went through all the diodes. Okay, so the diode current now is 5.8 milliamperes. Now this decrease in diode current will reduce the V naught as well. So decrease in ID will reduce V naught. So the change in V naught will be equals to minus 2.1 volts. Sorry. Okay, so the change in so the first thing is that there's a decrease in ID, so that will have a corresponding decrease in V naught. So delta V naught is going to be a decrease in V naught by 2.1 milliamperes multiplied by the total small signal resistance, which was 9.6 ohms. So the total reduction is going to be almost equals to 20 millivolts. And negative sign here shows decrease in voltage. right? So negative sign over here, it shows a decrease in voltage. And so this will be a total reduction across all the three diodes. All three diodes, right? So reduction across single diode will be equals to reduction across single diode will be equals to, we're gonna have 20 millivolts divided by 3. The answer is gonna come out to be 6.7 millivolts. So that will be a reduction across or across a single diode. Now we see that in terms of, so this particular voltage regulator circuit is performing much better in terms of catering for the changes in the power supply voltages. We saw that it is a 10% voltage. There is a very small reduction of around 0.5%. However, it is not catering as well for the changes in the variation in the load current. So anyways, one of the things to consider. So so this kind of finishes our lecture. In this lecture we talked about how we can use these diode circuits and develop these voltage regulators, in which we are interested in keeping our output voltage constant no matter what. And for any variations in the power supply that is feeding the circuit, or for any variations in the load that will end up drawing more or less current, our output voltage should remain the same. That is the purpose of a voltage regulator. Okay, so we're gonna further build on that and discuss another type of a diode, a special diode that is specifically designed for voltage regulation, called as a Zener diode. So we will see that, and we're gonna another interesting thing that we are going to see that in the next lecture is that we are going to use those Zener diodes not in the forward condition. Over here in today's lecture examples, we use the diodes for voltage regulation in the forward bias condition. We will use the Zener diode that we will discuss in the next lecture in the reverse breakdown region, and we'll develop the voltage regulator circuits, and we will realize that those voltage regulator circuits are even better in terms of voltage regulation. All right, so with that, this finishes up our lecture today. I will talk with you in the next lecture. Thank you so much. Bye-bye.